Hello everyone, welcome back. Let's solve this problem based on the combined loading. So this particular problem is asking us to determine that first of all, if this is a pressure vessel, and then the pressure vessel head is fabricated by welding the circular plate. So this is basically this circular plate. Okay, so that circular plate is welded, and if the vessel sustain an internal pressure 450 kilopascal, determine the average shear stress and in the weld location at the welding, and then state of the stress in the wall of the vessel. So since it's a thin wall pressure vessel, that means we have to get shear stress as well as sigma 1 and sigma 2, which we learned from the thin wall pressure vessel theory. Okay, so first of all, what I'm gonna do is that list that known. What are the knowns for this particular problem? So we know that the radius for this, this cylinder, basically the diameter is given, which is 450 right here. That means radius is 450 divided by 2, which is 225 millimeter, right? And then the thickness of the wall is 20 millimeter. And if we draw this diagram, free body diagram of this cap right here, which is welded, then it will gonna look something like this, right? So this section or this surface, right, basically experiencing the shear stress, which is tau average. And then the bottom surface is basically experiencing, maybe in different color, the pressure, right, that which is 450 kilopascal pressure. So we do have the pressure as well for this particular problem, pressure 450 kilopascal. And then what else? We do have this height, which is, let's say this h, we got this height 10 millimeter. So certainly we have to do the conversion of this unit millimeter to meter. But even before solving this problem, what I would do first thing is that check whether, whether this problem belongs to the thin wall pressure vessel or not. Okay, so check is that r divided by t has to be greater than 10, right? So we do have r 225 divided by the thickness is 20 millimeter, right? So it would be 225 11.25, which is greater than 10. That means yes, we can use the theory for a thin wall pressure vessel. Okay, so let's look at this cap, because this cap is basically welded, right? So now if we look at this cap, we do see that the shear stress is acting, stress is acting in this direction, right? Shear stress. And we also do see that the pressure is acting outward. Basically pressure force is, if the pressure is acting, trying to burst this thing, then the shear force is acting straight downward, right? So now we, at that interface, shear force is acting. Now if we do the force balance for this free body diagram, for free body diagram here, then of this cap, then if we do the force balance for vertical direction, let's say Fy equals to 0, summation of Fy in upward direction is positive, then we know that the force due to that pressure is nothing but pressure times the area, right? Which is, let's say I'm writing this one, pressure times area minus this shear stress tau average times AVZ times the area as well. And this area is different because this area is basically the strip surface, or this cap surface. Okay, so equals to 0. So now the pressure is acting, which is 450 kilopascal. Let's convert it in pascal, which is 10 to the power 3 times the area of this section, basically area of this, this cross section, or the inside or inside surface would be pi r square, right, which is pi times r square. So we got r equals to 225 millimeter. If we convert it in meter, then it should be 0.225 meter. Okay, so we got that one, pi r square. And tau average, we know, we actually don't know tau average, right? We have to determine that one, times the area. So what is the area of this, this strip? So this area of this strip is basically the total length of that strip twice pi times the r, which is 0.225, times the height, which is 10 millimeter. In meter it would be 0.01. Okay, which is equals to 0. So if we solve this for the tau average, or shear stress would be 5.06 into 10 to the power 6 pascal, or Newton per meter square, right? So what we're gonna do is that, let's say we are taking we're taking this pascal, and then tau average would be 5.06 megapascal, right? So we already got the shear stress, average shear stress. So this is our answer 1. Now they also asked us to determine what state of the stress in the wall of the vessel. We already saw that this is belongs to the thin wall pressure vessel, right? By this condition, now we know those formula. So we know that for hoop stress, which is sigma 1 equals to PR divided by T. So pressure for this particular problem, 450 into 10 to the power 3 pascal times the radius 0.225 divided by the thickness was 20 millimeter, which is 0.02. So if we solve this for sigma 1, we'll get 5.06 megapascal as well. Okay, and then we know the formula for longitudinal stress. Which is sigma 2 is PR divided by 2T, which is 450 into 10 to the power 3 times 0.225, 2 times the thickness, which is wall thickness, which is 0.02. Again, sigma 2 would be 2.53 megapascal. Now we can either do this way, or simply sigma 2 would be half of sigma 1, right, which is 2.53 megapascal, because we know that the longitudinal stress is half of the hoop stress. Okay, so that's all is our answer. So this is the answer for sigma 2, and this is the answer for sigma 1. So yes, we did see that even if it is a cylindrical a thin wall pressure vessel, cylindrical vessel, but if we do the welding, we could see that combined loading. That means it may have the shear stress at this interface. Also, we can have the stresses in longitudinal direction, also in circumferential direction. So by all means, it is a combined load problem. All right, that's all for this problem. Thanks for watching this video.